Hello everyone, today we are going to start with chapter 1 of grade 10 maths, real numbers. What are real numbers? We've already done it in our previous classes that real number, they are a set of rational as well as irrational numbers. We have learnt rational numbers are those which can be represented in the form of p upon q, where the denominator q is not equal to 0. On the other hand, the numbers which cannot be represented in the form of p upon q are not rational numbers, they are known as irrational numbers. So when rational and irrational numbers are grouped together, they form a set of real numbers. Now under this chapter, real numbers, will be studying some important properties of real numbers, the first being Euclid's division lemma. Euclid's division lemma is a very important concept as it helps us, because it has already helped us to find the concept of HCF and LCM and also division algorithm. Let us try to understand Euclid's division lemma by taking this very simple example. Suppose we have 63 pencils to be arranged in 5 boxes. We have 63 pencils and 5 boxes, and the number of pencil in each box is 12. Each box has a capacity to hold 12 pencils. Also, we have 86 erasers, 32 sharpeners and 10 ball pens to be arranged in 8 boxes. So, 86 erasers to be arranged in 8 boxes, and the capacity of each box is holding 10 items. Similarly, we have 32 sharpeners to be arranged in 4 boxes, and the capacity of each box is 8. We have 0 boxes for 10 ball pens, they have to be kept loose, and the capacity of each box, if it was there, was supposed to be 15. So if I arrange it in the form of a table, because all these numbers are looking very complicated, let us tabulate them in a systematic manner. Pencils, how many pencils each box can hold? 12. How many erasers each box can hold? 10. How many sharpeners each box can hold? 8. How many ball pens each box can hold is 15. How many boxes do we have? We have 5 boxes for pencils, we have 8 boxes for erasers, we have 4 boxes for sharpeners, and we have no boxes for ball pens. They have to be kept loose. Now let us come back to the number of erasers, sharpeners, pencils and ball points that we have. We have 63 pencils. Since we have 63 pencils and 5 boxes, each box holding 12 pencils, obviously 3 pencils would be left extra. There will be no place for the remaining 3 pencils to be put in the box. Similarly, we have 86 erasers, but there are only 8 boxes, each holding 10 erasers, and as such, how many erasers will be left? Yes, 6 erasers would be left loose, not fitting in the box. Similarly, we can see we have 32 sharpeners, and these 32 sharpeners have to be arranged in 4 boxes, and it will fit exactly, because since each box is holding 8 sharpeners and there are 4 sharpeners, 8 into 4 will give me 32, and there will be no sharpener left. So as we can see, the leftover is, or the extra item which has to be kept loose, is 0. Next, how many ball pens do we have? We have 10 ball pens, and there are no boxes for it. So since there are no boxes for it, 10 ball pens will have to be left loose as an extra item. If I add the leftovers to the items packed in the box, that will give me the total. So the total number of pencil has come to be 63. And how did we get it? 12 into 5 plus the extra. 12 into 5 pencils in the box and 3 extra has given me 63. Similarly, 10 into 8 plus 6 has given me 86, and 8 into 4 plus 0 has given me 32. 15 into 0 plus 10 has given me the total item as 10. Let us generalize this rule and see whether this rule holds true in other situations also. We have just seen this arrangement, how to find the total item, the leftover, and the total item and the leftover items. So how did we get it? The first column multiplied by the second column plus the third column has given me the total, and it is true for each of the column. It is true for each of the column. So if I generalize this, how do I generalize this for all numbers and all situations? If I consider the pieces per box, the pieces of item per box, if I denote it by an integer b, because these are items and numbers, they have to be positive integers. It is very, very important. These numbers cannot be negative, because if we are taking some real life example, the materials cannot be negative. The objects have to be positive in number. Number of boxes 5, 8, 4 and 0, and let us denote the number of boxes by Q. Extra items by R and the total by A. So what do we see, that how did we get A? In every column and in every row, the same rule has been applied. What is the rule? The first multiplied by the second added to the third is giving me the fourth column. So if I generalize it, I will write A is equal to B into Q plus R. So this is my Euclid's division lemma, which is derived like this. And what does it state? That any real number, any real positive number A can be broken up, or it can be broken up as B into Q plus R, where B, as per this example, is the number of items per box, Q is the number of boxes, and R is the leftover. So we have been doing this all through while doing division also, that I consider this A to be my dividend. Dividend is always equal to quotient into divisor plus the leftover remainder. Let us now understand that how Euclid's division lemma helps us to solve our day-to-day problems. One of the most important application of Euclid's division lemma is to find the highest common factor. Let us try to understand this using this simple example. Here it's given Mr. Avaditya has 520 boxes of chocolates and 140 boxes of balloons to be arranged in least number of shelves, so that each shelf has equal number of balloons and boxes of chocolates. Boxes of balloons and boxes of chocolates have to be arranged in equal number in each of the shelf, and we have to also look for the least number of shelves. Least number of shelves, but least number of shelves will be available only when the maximum is fit into each shelf. So here, to begin with, 520 and 140 as numbers, what we will do, first we will split up 520 as a factor, or as a multiple rather, as a multiple of 140. I have to split up 520 into multiple of 140, 140 being one of the factors. If I write it as 520 is a multiple of 140. I know 520 is not an exact multiple of 140. So, the least number with which 140 can be multiplied is 3. 140 into 3 will give me 420, but to make it 520, 100 more has to be added. Now, this 140 will again be divided using 100 as one of the factors. So, 100 into 1 will give me 100, but the number is 140, so 40 more has to be added. Again, I will divide this 100 using the leftover number 40. 40 into 2 will give you 80, because 100 is not an exact multiple of 40. So, 40 into 2 will give you 80. 80 plus 20 makes it a complete 100. Next step, I will use this 40, and this 40 will be divided by 20. 20 multiplied by 2 will give you 40 plus, since it's complete 40, the leftover will be 0. So, what do we see? We start with the bigger number 520 and divide it using the smaller number among the two, and the leftover number is 100. So, using Euclid's division lemma, this is my A, this is my B, this is Q, and this is R. Again, R becomes my dividend in the next step. 140 equal to 100 into 1 plus 40. 100 into 1 plus 40. Next step, this 100 will be divided using 40, and the leftover is 20. Next step, 40 will be divided again by the leftover 20, and the remainder is 0. So, in the entire process, what do we see? We divide the first number B by the leftover. 520 divided by 140. In the next step, 140 will be divided by the leftover. Next step, 100 will be divided by the leftover. So, every time we keep on doing this until we get the value of R as 0. We continue doing this until we get the value of R equal to 0. So, that divisor, which is the divisor which is giving me the value of R equal to 0, 20. 20 is the highest common factor of 520 and 140. So, this is the maximum number of chocolates boxes and the balloon boxes that can be arranged in least number of shelves. And what are the number of shelves? The number of shelves can also be calculated using this. So, let A is equal to 520 and B equal to 140. 520 can be split up as factors as 140 into 3. The leftover is 100. Now, this 140 is again divided by 100 to give me 40 as the remainder. Next, 100 is again divided by 40 to give 20 as the remainder. 40 is again divided by 20 to give 0 as the remainder. So, with this we come to remainder 0. So, by Euclid's division lemma, HCF of 520 and 140 is 20. What was the question? Mr. Aditya has 520 boxes of chocolates and 140 boxes of balloons to be arranged in least number of shelves, that each shelf has equal number of boxes of chocolates and balloons. So if we have 20 as the HCF of 520 and 140. So in each shelf 20 will be arranged, 20 boxes of chocolates and 20 boxes of balloons. So we have learnt how to calculate the HCF of the two positive integers. Given two positive integers A and B such that A is greater than B, in our case 520 was greater than 140. Apply Euclid's division lemma. We have seen we have divided 520 as 140 into 3 plus 100 in the first step, where A was my 520, B was 140, Q was 140 into 3 plus R. So we keep on splitting it into factors until we get the value of R equal to 0. So we continue the process till R becomes 0. The divisor B in that case is the HCF of the two given numbers. Now, moving further, we have another question. Show that every positive odd integer is of the form 2q plus 1. This is a very important and the most common question that we get in our examination in the real numbers chapter. Let A be any positive odd integer. By Euclid's division lemma, I can break up A as B into Q plus R. We have to show that every positive integer, odd integer, will take the form 2q plus 1. For this, we start with let B equal to 2. What is B? B is my divisor. So if I, in the given equation, A is equal to BQ plus R, if I put B equal to 2, then A is equal to 2Q plus R, and R always lies between 0 and B. R is greater than equal to 0 and less than B. So in that case, if B is 2, R will take only two values, 0 and 1. So the two possible values of A will be 2q plus 0 or 2q plus 1. A is not equal to 2q since 2q is divisible by 2 and A is an odd number. So we do not take this option, A is equal to 2q, we let go this option and the other option left is 2q plus 1. Thus, any positive odd integer can be represented in the form of 2q plus 1. This can be carried forward. This we may have several questions of the same type. Sometimes you may be asked to prove that every positive integer, odd integer, which is a multiple of 3, is of the form 3q plus 1. So what did we learn in this chapter? Euclid's division lemma states that any two positive integers, A and B, for any two positive integers, we can find two whole numbers, Q and R, such that this relationship A is equal to BQ plus R, where R lies between 0 and less than B, R greater than equal to 0 and less than B, R will have all the values positive. Greater than equal to 0 means positive and less than B. And it can be used to find the highest common factor of any two positive integers and show the common properties of numbers. Next, we come to fundamental theorem of arithmetic. What does the fundamental theorem of arithmetic state? The fundamental theorem of arithmetic states that every composite number can be expressed as a product of prime numbers, and this we have been doing it. We have done it using prime factorization or factor tree method in our previous classes.
To watch the complete video, download the Upbind educational app from Play Store and App Store.